Hello, everybody. Let us talk about state collapse in quantum mechanics. Because when we perform the measurement in quantum mechanics, the quantum state will collapse, and the state will collapse to one of the eigenstates corresponding to the eigenvalues for the particular property that we are trying to measure. Now, in that case, let us say a cap is the operator or the observable that we are trying to measure in a quantum system. In that case, a operator or observable will have eigenvalues given by a set of lambda n values, right? And corresponding to each eigenvalue, there will be an eigenvector, and that eigenvector is represented by ket un corresponding to each one of the eigenvalues, right? And this eigenvector will be termed as the eigenstate here in this case. So overall, this becomes the eigen equation for a quantum system when we are trying to measure the quantum system for observable A. So this is eigenvalue equation for operator or observable A. Any operator which can be measured will be termed as the observable. Now, if the measurement of the observable A of a system in state ket psi. Now, what is ket psi? Ket psi is the state in which the quantum system is. A cap is the observable that we are trying to measure. So that's why it is being said here that if the measurement of observable A of a system in state ket psi gives eigenvalue lambda n, the system will collapse to eigenstate ket un corresponding to lambda n. So once we try to measure the quantum system or the observable A cap, when the system is in state ket psi, the state of the quantum system from ket psi will collapse to the eigenstate. Now, what is that eigenstate? That eigenstate is an eigenvector corresponding to the eigenvalue that we are measuring, and corresponding to that eigenvalue eigenvector ket un will be there, and this eigenvector will be called as the eigenstate. So therefore it is diagrammatically is also shown here. So at the start you have the quantum system in state ket psi, you measure observable A. So observable A will have n eigenvalues. Now when we measure because the measurement will be probabilistic and we will get one eigenvalue. So one eigenvalue will correspond to one eigenstate. Ultimately, the quantum state ket psi will be collapsed to ket un. So this is known as state collapse. It means that ket psi after measurement A will collapse to eigenstate ket un. Expectation value. So let us talk about, because I want to describe the concepts of expectation value and the measurement outcome. So we have to deal with two things. One is measurement outcome, the other is the expectation value. So we also want to know whether the expectation value is the same as the measurement outcome or not. So let us try to dig deep into this concept. Expectation value is a concept borrowed from basic probability theory, and it allows us to characterize the probability distributions. These are useful in quantum mechanics because we know that the information captured by the quantum state can be represented by a probability distribution. So we know that information about the quantum system, quantum state can be represented by a probability distribution. For example, when we are trying to measure the observable A, it will have n eigenvalues. Now, at the time of measurement, what measurement outcome will be there? It will be one of the eigenvalues. But since the measurement in quantum systems is probabilistic in nature, so therefore there will be a probability attached to each eigen value. That means if the measurement outcome is this lambda n, so there will be a probability p lambda n attached to this measurement outcome. In the same way, all the eigenvalues will have a probability attached, that with this probability this outcome at the time of measurement can come, right? So uh, that's why, because we know, that's why I say that information captured by the quantum state can be represented by a probability distribution. If we have to However, we have to be careful when using expectation values in quantum mechanics, because these are often confused with the measurement outcomes. It should not be so. Expectation value is not the same as the measurement outcome. So we cannot confuse one. If we know the expectation value, we cannot say that this is the measurement outcome at each every measurement, right? So we have to distinguish these two quantities or entities. Now it is important to realize that the expectation values and the outcomes of measurements are two completely different things in quantum mechanics. Quantum mechanics does not tell us the precise outcome measurement as I have just described, because the quantum mechanics measurement is probabilistic in nature. So therefore, it does not tell us the precise outcome of the measurement, that this is the particular measurement outcome that will happen. But when we are measuring in quantum mechanics, what we at the most what we can say, that with this much probability the measurement outcome can be. Therefore, but it tells us about the probability associated with that outcome. Another way of understanding this probabilistic interpretation is to imagine that we have many copies of the system. Let us imagine that we have many copies of the system in state cat psi. For example, we measure the system. So at one time it gives lambda 2, at another time it gives lambda 1, lambda 1. So let us say lambda n appears pn times, and let us say we measure number of times we measure the quantum state is capital N. So therefore Pn by capital N is the probability that we will get lambda n as the measurement outcome. So when n is approaching infinity, this experimental probability of Pn times that we can get lambda n divided by the total number of measurement attempts will be equal to probability lambda. So this we can say is the theoretical probability, and this is the experimental probability. So if n is greater than n is approaching infinity, so this experimental probability will approach towards the statistical probability, right? So ultimately measurement is a probabilistic concept, right? And what outcome the system will have after measurement is probabilistic in nature. Now let us try to understand expectation values and one other quantity we will discuss, and that is root mean square deviation. So let us understand the expectation value first. Along the x-axis are the eigenvalues of the observable A. Along the y-axis is the probability of each eigenvalue. So therefore, if the measurement outcome is lambda 1, so probability associated with lambda 1 is modulus of C1 square. With lambda 2 is mod C2 square, magnitude squared of C2. Lambda 3, corresponding to lambda 3, it is mod C3 squared magnitude basically of C3, and so on for each eigenvalue. What are C1, C2, C3? These are expansion coefficients. We know that because we know that we can express a quantum state as a linear combination of the eigenbases. So Cn's are the expansion coefficients. And how do you calculate Cn? Cn will be calculated as a projection of psi on un, right? So that means the overlap between un and psi will give me the expansion coefficient. Un is basically the eigenvector corresponding to that eigenvalue. And if you use the eigenvalue equation, this is the same thing. I'm just trying to explain that probability of lambda n, probability of any eigenvalue will be equal to magnitude squared of the expansion coefficient Cn. Now this diagram, the above diagram, this particular diagram that I have just shown, This diagram shows the probability distribution. So higher the height of this p lambda n, more likely we will measure that particular item or that particular outcome. Now let us take a special case when the state of the quantum system is already one of the eigenstates, right, before measurement, and when the state of the quantum system is one of the eigenstates, and if let us try to measure this now. So if it is one of the eigenstates, so definitely it will get the eigenvalue, it will get lambda m, which is the eigenvalue corresponding to this eigenvector or eigenstate. We will definitely get this measurement outcome. That means this eigenvalue will be the measurement outcome, right? And in that case, the probability will be equal to 1, and the quantum state after collapse will be ket um, which is the eigenstate corresponding to this eigenvalue. So that is, there is a 100% certainty that the outcome of the measurement is known if the system is in eigenstate of the property that we are measuring, right? So this is a special case basically. Then the outcome of the measurement will be associated eigenvalue with probability 1. So this is the lambda. In the diagram I am showing, in the diagram between eigenvalues and the probability, if the quantum system is in eigenstate ket um, so definitely the measurement outcome will be lambda m. So that's why I am showing this lambda m with a probability 1 in the probability eigenvalue curve or probability distribution. So therefore, probability distributions can sometimes be very complex, which make them cumbersome to work with and many times can obscure understanding. In that situation, what we do is to define a number of quantities that will allow us to simplify the information and then code it in a probability distribution. So that means we are assigning some statistical parameters to a probability distribution if the probability distribution becomes complex. Now this will come at a price of losing some information, but the resulting quantities are very useful in many problems. The first quantity that we will define to characterize the probability distribution is the expectation value. So we will try to define the expectation value, but ultimately it is not the measurement outcome. While defining the expectation value, it is definitely very helpful in many decision making, but see, we are losing information when we are trying to relate things with the expectation value, right? So let us define this term expectation value. This is the average value of measurement outcomes. Now consider a system in state psi. The expectation value of an observable A is written as, so this is how two angled brackets, this is how we denote the expectation value of observable A when the quantum system is in state psi. Or we can simply remove this state psi from here and we can use the two angle brackets and the observable. So this will be the expectation value of observable A, and this is defined as lambda n, probability of lambda n, and we will sum for all the eigenvalues. All the eigenvalues multiplied by their probabilities and summed up will give me the expectation value, right? And probabilities, we know that it's a projection of u on the, it's a projection of psi on the eigenspace, right? So this is magnitude squared. This is from Born's rule, we know that. So this is how the expectation value is calculated. Expectation value is also can be defined by this matrix entity type of quantity, which says that it's the inner product of this expression inside. So using this expression, you just manipulate it by inserting the identity here and identity here. So for this identity, I can put the summation of the outer product of this. This is identity, we know that. This is again identity for two different eigenstates. So if we further manipulate it and use the eigenvalue equation, so this A ket um will be equal to lambda m ket um. So we replace this part with this lambda. So we'll take lambda m out, and ultimately what we are left with this term. So this is inner product between um and un. So this will be equal to delta, canonical delta for n comma m. This will be equal to 1 when n is equal to m, or this will be equal to 0 when n is not equal to m. So in that case, if you just use the, if you use the square term, so what we will do is, there are see, this is one term, psi of um, and this is of course the canonical delta, right? And when n is equal to m, this will be equal to 1, and so therefore only, so there will be summation only for n when n is equal to m. In that case, this will become 1, and there are two quantities which are squared of, which can be squared. So this is equal to lambda and um. So if you remember, we defined the expectation value to, and we defined it to be equal to this, and when we started with this entity, so we got the same expectation value. So therefore the expectation value of an observable can be defined with this expression or with this expression, right? Now it is proved that we can indeed write the expectation value as this term. Just I have explained this, and we typically work with normalized state. Since we typically work with normalized states, so we will have to do the normalization, and that normalization will be done by the norm, and norm will be obtained by taking the inner product of the psi with itself. Now this is important point here, very important point actually. From this point, talking about this point only, I started with this lecture, in which I said that the measurement outcome should not be confused with the expectation value. That's what I'm trying to explore it further. We should never confuse the expectation values as the outcome values. That is, consider a system in cat psi. So let us consider a system in cat psi state. What value shall we get when we measure A? So that will be the measurement outcome. If we say that it is the expectation value, then it's a wrong answer, absolutely wrong answer. And I will make the case, make certain cases where it will be proved that the expectation values cannot be used as the measurement outcome. So the value that we will get is one of the eigenvalues of this set of eigenvalues. Out of the set of eigenvalues, the measurement outcome will be one of the eigenvalues. So we know that that comes from the postulate of quantum mechanics, but we cannot know which value we will get, because the measurement is, as I have repeatedly said, is a probabilistic concept. We cannot with 100% certainty say that this is the measurement outcome when the quantum system is in state cat psi. That means it is not it is not in the eigenstate. So it is a superposition state. So we cannot say what measurement outcome we will get, but we can only say with certain probability that with this probability, each measurement outcome. So we can attach a probability distribution with the eigenvalue set. So we can know this probability distribution, that is probability associated with each lambda n value. Now consider an example here. Consider a 2D state space of a system, and we can write the eigenvalue equations for the two states corresponding to two eigenvalues. So let's say a 2D quantum system is there, in which the quantum system has got two eigenvalues. One is +1, the other is -1. For +1, the eigenstate is u subscript plus, and for -1, the eigenstate is, let's say, u subscript -1. So if that is the case, we can write the eigenvalue equations like this, and we can also say that the cat psi state, which is a superposition of the eigenstates, we can write it to be like this. This 1 over under root 2 factor is there to ensure the normalization. And when we measure A, because this is uniform, this is equal superposition, that means +1 or -1 eigenvalue will be with probability half with each. That means probability of getting eigenvalue of getting measurement outcome +1 is half, of getting -1 is also half. So I draw the probability distribution diagram, between the probability values corresponding to each eigenvalue, and along x-axis is the eigenvalues. So two eigenvalues as I just described, one is -1, the other is +1, and with half with probability of -1 as the eigenvalue is half, probability of +1 as the eigenvalue is also half. And if we take the expectation value will come out to be 0, right? And but we know that the measurement outcome can be either -1 or +1, which has nothing to do with this 0. So that proves the point when I say that the expectation value cannot be confused with the measurement outcome. This is a simple system which explains the that why can't we use expectation value in lieu of the measurement outcome. Though expectation value is an important term that provides a lot of useful information, but measurement outcome comes from the postulates of quantum mechanics, not from the expectation value. So the result of measurement can be either +1 or -1, but the expectation value is 0. So therefore it is clear that expectation value does not tell anything about the outcome of a particular measurement. This is what just I was trying to explain. Another term that we will define is the mean square deviation. Because the expectation value gives a particular value, but it does not give us the spread of the probability distributions. So that I will also explain that why expectation value does not come up to the expectations of the quantum computing designer. So he needs another term, which is the mean square deviation, to describe the probability distributions. So let us define this term. This term is sigma subscript a, and this term is known as mean square deviation. Mean square deviation. So it is given by the observable a minus the expectation value of the observable a. And if we square it, so this is the normal deviation without squaring of the observable a from its expected value, right? But if we square the expectation value, this term becomes the mean square deviation, because mean is also there, square is there. So deviation we are trying to know, it is given by the square of this term. If you open the square, you will get this expression, and using this concept of that expectation value of a scalar is the scalar value itself, then if we use this manipulation, we will get this mean square deviation to be equal to this expectation of a square minus expectation square of a. These are two different terms, we must understand. The quantity which is typically used to measure the width of the distribution. So this quantity will be used to measure the width of the probability distribution, that how much is the spread of this distribution. The quantity which is typically used to measure the width of the distribution, so therefore it is the this is mean square deviation, but the quantity that we actually use in the measurement of the spread is the root mean square deviation. So what is root mean square is just take the under root of this, so that will be equal to delta a, which is called as root mean square deviation. Root mean square is this, mean square deviation is this, so this delta a becomes the root mean square deviation. So that is under root of this mean square deviation, and this is the quantity which is root mean square deviation. So let me try to explain. See, this is a very interesting diagram in which you have two probability distributions. One is P1, the other is P2. Both the distributions have got the same expectation value, and it is it is given by this A. I mean the angle brackets, in the angle brackets is observable A, so this is the expectation value of A. So expectation value of both the probability distributions is the same, but you see the width is different. W2 is the width for probability distribution 2, and W1 is the width for probability distribution 1. So therefore, expectation value, we cannot say, knowing the expectation value, the characteristics of the probability distribution, because P1 and P2 are two different probability distributions. Though the expectation value is same, but this root mean square deviation is different, which explains the width of this distribution. And this mean square deviation looks at how far we are from the average. That is very correct. This spread will look for how far we are from away from the average. And let us take a special case in which the cat psi is one of the eigenstates. In that case, the expectation value will be equal to the eigenvalue, and if we try to find out this root mean square deviation, it will come out to be 0 in this case, when the quantum state is one of the eigenstates. So that's why if it is showing if this quantity delta A is showing the spread, let me just write it here so that, okay, so this becomes delta A, and delta A is approaching to 0, right, when the quantum state is one of the eigenstates. So that's just the diagrammatic representation of the case when the quantum state is one of the eigenstates. So this finishes my lecture uh, on expectation values, measurement outcomes, and mean square deviation or root mean square deviation. We will continue with the more topics. Thank you.